So today's focus is going to be on cells and batteries. In other words, how we can store electricity to later be used to provide a current, to provide power to the things we need it to provide power for. So anyway, let's get going. We're going to look at the ways that electrical energy is stored for later use in current electricity, cells and batteries. We're going to talk about the difference between cells and batteries because oftentimes in day-to-day use, they're often used interchangeably. That's not the case when you actually look at it. We'll talk about the type of cells. There's dry cells and wet cells, and then we'll also talk about rechargeable cells, as well as electrochemistry, where there's a whole bunch of different things we have to talk about with that. Anyway, let's get going. So an electric cell is something that can change one form of energy, so usually chemical energy, into electrical energy, right? So a cell is just something that provides that electrical power for us. Now, an electric battery is made up of one or more cells and is used to power electrical devices. So there's only a subtle difference between a cell and a battery, and it's that a battery is actually usually made up of more than one. And of course, a battery is what's used to provide the power we need for things. So for instance, you might not be aware of this, and please, by all means, do not try cutting one open because that can cause a lot of damage and a lot of trouble. But if you took a 9-volt battery and you were able to cut it open, you'd actually find that inside the 9-volt battery are 6 little cells, right? Now, these little cells kind of look like AAA batteries or something. They're not, actually, but they are cells that provide a similar function to that, right? So a battery like this one is just made up of a bunch of little cells that, of course, each individually provide the power needed to power that battery. This other one we see on the left, however, this is an example of a car battery. Car batteries work under the same general principle as other batteries do, but of course, they're just laid out a little bit differently. But the cells are still something that exists inside of it. If you were to cut open a car battery, which I would highly recommend against doing, do not do that. You'd find that there's a bunch of little cells and they're all divided by different dividers, right? So cells, of course, are just little packets that are converting some sort of chemical energy into electrical energy. All right, so first of all, we'll look at dry cells. So dry cells include the AA and AAA batteries that we use in many day-to-day things. A dry cell is a type of cell where the chemicals that store the energy are actually in a paste. So in other words, they're dry, right? Now that paste is often called an electrolyte. An electrolyte is just something that carries electricity through it, right? So it's just a very fancy way of saying that. Now, they are also totally sealed so that chemicals won't leak out. And they can be used in any position. You can put them right side up, upside down, sideways, whatever. Those chemicals inside of there, that paste, isn't going to leak out unless you were to cut it open or something, which again, really, really bad idea. You do not want to be doing that. Now, how these work, of course, is there's a chemical reaction that occurs between the electrolyte and the electrodes, which are metals in the cell, and that releases electrons down here at the negative terminal. Right? So in amongst all this paste, the paste is kind of the grayish kind of color stuff in here. The paste is reacting with a metal that's within inside of this. And of course, that chemical reaction is releasing electrons, which get caught up in this, this rod that's right here, and then they shoot out the negative end of the battery. Remember, electrons are what's moving here. It's not the positive charges that are moving, it's the negative charges that are moving. So the electricity is really coming from the negative end. The positive end just serves as a way of collecting it. And of course, there's kind of like a buffer region that's made of manganese dioxide, at least in this battery, that kind of collects and buffers those returning electrons. Now, when the electrolyte or electrodes, kind of messed that one up, when the electrolyte or electrodes can no longer perform that chemical reaction, we say that the cell or the battery is therefore dead, right? So in other words, when that chemical reaction can't happen anymore, that's it, it's over, the battery is dead, right? So you'd have to throw it out or get a new one or whatever, right? All right, wet cells. This is a different type of cell, of course. Obviously, by the name, these cells are wet. They have a liquid in them, right? So the electrolyte, what carries the electricity, is a liquid. As a matter of fact, it's usually some sort of acid. That's why you've probably heard of before battery acid. Battery acid, of course, is acid inside of a battery. Big surprise, right? Now, the electrodes, however, are solids within this. They're usually like little plates that are put really close together. In most wet cells, how it generally works is these plates that make up the cells themselves alternate between being a positive and a negative electrode, right? So in other words, they have a different, polarized note to them, right? So in other words, one will be positive, one's negative, and they alternate, okay? Now, in the early days of cells and batteries, all cells were wet cells, right? So wet cells were the first ones to really be made with this, and there still is an explanation as to why they were the first one, because we still use them to this day. And we use them because they are easier to make and they're cheaper, right? So the things that are easier to make and cheaper, generally speaking, are probably the ones that were designed first. right? Now, one concern, however, is if the liquid electrolyte spills, because that can be very corrosive. You don't want battery acid leaking out onto something, especially onto your skin or something like that. So of course, wet cells do have a risk inherent to them, but they are easier and cheaper to make. Now, generally speaking, the reason we don't use wet cells in things like your TV remote, which would take normal dry cell batteries, is because, of course, with the liquid inside of them, there is always a risk of that liquid spilling out somehow. Now, a car battery is a wet cell, but this is totally fine in a car because there's no risk of the car, or at least there's very, very little risk of the car ever being in a position where that battery acid's going to leak out, right? Generally speaking, your car is just going to be straight up unless you're going up and down a hill. Even then, it's only on a slight incline. There's not really a risk in those cases of this liquid spilling out. Now, yes, these are sealed off. Yes, they shouldn't spill. But again, you don't want to be making any chances there, not to mention if there wasn't enough liquid in here and during contact with these electrodes down here, you didn't have perfect, thorough contact, the cell wouldn't work as well as it would be intended to, right? Anyway, moving on. So this picture right here is actually a picture of a very simple wet cell. So when you look, I'll just go back, when you look at something like a car battery, this is a lot more complicated. These electrodes in here are pretty close together, and it's kind of hard to see what's really going on here. But if we look at this, this is about as simple of a wet cell as you can produce. Just to break it down here, you have two electrodes, and they've used different materials for each one. So this one on the right is made of zinc, and this one on the left is made of copper. Now what happens is, there's a solution that both of these electrodes are placed into, and you'll notice that the solution is actually a type of acid, sulfuric acid. Now, this sulfuric acid serves as an electrolyte. The electrolyte is something that's going to help us carry electrons. When both of these electrodes are placed in here, a chemical reaction occurs. As you can see, there's hydrogen gas bubbles being produced at the copper electrode. And because of the chemical reaction, there's going to be some electrons that start buzzing through this. If we connect it up with a circuit, so some sort of wire conductor, and then even a load that they've put on here, they've put a light on there, you're actually going to find that there is some electricity flowing through there. And if there's enough, then you'll find that this light will actually turn on. And that's because this situation that we see down here in this beaker with the acid and the two electrodes in it, that right there is a very simple wet cell battery. So it's like this component on its own is serving as a battery to power this light source. Okay, moving on. All right, rechargeable batteries. I'm not going to spend a long time on this because it's not super important. Basically, with rechargeable cells, such as lithium-ion cells that are used in pretty much every phone today and most other like rechargeable devices, the chemical reaction that's producing that electrical energy can actually be reversed simply by reversing the flow of electrons. So in other words, when you use it regularly, there's a discharge, right? Because you're discharging your battery by using it, and the electrons are flowing a certain way. And in this diagram, it might be hard to see, but the electrons are flowing that way. But when you reverse the flow of electrons, in other words, if you plug it into the wall, we can make the electrons go the other way. And when that happens, the chemical reaction that usually occurs within this cell gets reversed, right? So in other words, it gets undone. Now, however, I need to just point out to you, reversing a chemical reaction, it's not always perfect. This is why after many charging and discharging cycles, the rechargeable cells don't last as long as they used to. So after you've had something several years and you've recharged it like 1,000,000 times, it's not going to hold the charge like it did the day you bought it, right? All right, moving on. All right, next up, electrochemistry. This is where things get even more interesting. Electrochemistry is the study of chemical reactions that involve electricity. They can either be chemical reactions that produce electricity or chemical reactions that occur because of electricity, okay? You can go both ways. There was an Italian scientist named Alessandro Volta, and you're probably not super surprised by this, but he's the guy who the word volt comes from, right? So Alessandro Volta, he made the first type of battery called a voltaic pile. Now, basically, this was just a very simple wet cell battery, but it had several different cells connected through it, right? So we had alternating positive and negative plates, and there was an electrolyte that was found in between each of those plates, right? So that was serving as a way of getting those electrons to shoot through the whole system, right? Now, his discoveries led to the creation of the field of electrochemistry. So obtaining electrical energy from these types of chemical reactions is just one application of electrochemistry. There's many others. What I'm trying to say here is electrochemistry isn't just about analyzing wet cell batteries or even dry cell batteries. There's other things we can do with this. Some of them are actually pretty interesting. So one of these applications is something called electrolysis. So electrolysis is by using electricity, to separate solutions or even molecules into their components. Probably the simplest example, and the one that I always kind of do as a go-to experiment, is if you actually hook up some sort of a power source with a positive and a negative electrode to water that has a little bit of salt in it so that you can allow the electricity to flow through it. What will actually end up happening is, because of the presence of these two electrodes, there's going to be a chemical reaction that occurs at each of these two electrodes, the positive and the negative terminal. Oxygen bubbles are going to form at one, and hydrogen bubbles are going to form on the other. Now, this is significant because, of course, water is made of H2O. There's two hydrogen atoms and one oxygen atom. And so when you're passing an electric current through water, as long as there's a little bit of salt in it, this is actually going to force those molecules to get ripped to shreds to form their component pieces. Well, one component piece is hydrogen gas, which maybe if you remember from the chemistry unit, it's part of Hofbrinkel, as we said. It can't exist on its own. So you'll make H2 gas, and then you'll make oxygen gas, which is also part of Hofbrinkel, so it'll make O2 gas, right? So you'd have to actually combine many of these in an electrolysis reaction to produce two of the oxygens. It comes out of a chemical reaction. We're not going to get into that right now, but basically all you need to know is electrolysis is by using electricity to separate something into its parts. It doesn't have to be molecules. Sometimes they do this with solutions. So if you mix some things together, you could separate the thing that was mixed inside of it out of it. It doesn't actually have to be a full cohesive molecule. All right, next up, this one is my personal favorite, electroplating, which is probably exactly what it sounds like. It's using electricity to plate something, right? So in other words, this is used to coat a metal object with another metal, and that other metal is usually something that's more valuable, or at very least it's better looking, or just whatever you want it to look like. In this picture down here, someone took, I think this is a lighter, like an old-fashioned lighter. They took one that looks like it maybe had a brass plating, and they wanted it to have a nickel plating. So nickel's kind of like this silver color stuff right here. So they were able to use electroplating to turn it into a nickel-plated surface. Underneath that nickel surface is still the old brass that it was made of, right? So it's not changing what this thing was made of, it's just changing what it was coated with. So it's like adding like a coat of like paint onto it or something. It's just with metal, of course. Now, what's really interesting about this is, unlike paint, the metal actually never turned to a liquid or anything, right? So the metal stayed in solid form, but it just went from one location to another and ended up just on the surface of this. Electroplating is really mysterious, but it's actually pretty simple to set up. So here's how it works. Your source metal, so the one that you want to use to plate the other thing, so let's say in this case they plated this with nickel, they would have had some piece of nickel that they're just going to use as a throwaway, is connected to a positive electrode. So in other words, it's an electrode, or is connected to be a positive electrode, my mistake. In other words, it's connected to a positive terminal on a battery or a power source, right? So your source metal becomes your positive piece, and the metal that you want to get coated is connected to be a negative electrode. So in other words, they took this lighter or whatever it is, and they hooked it up to a negative end to turn it into a negative electrode. Now the ions from your source get transferred to the outside of the thing you want coated. They just immediately just like hop through the solution that they're in to go over to the thing that you want coated. I think it'd be better to see an actual picture of this. I'll show you. The one on the left, of course, is just a diagram showing how it works. Notice how they've hooked up the thing that they want to throw away. So their source is going to be the copper, and it's hooked up to a positive end of a battery. The thing that they want coated, which they just called Me for metal, so some metal that they want coated with copper, is hooked up to the negative end of a battery, right? So it becomes a negative electrode. What happens is the ions from this copper source go through some solution, and usually the solution is some form of acid, as this is right here. You can't really see that, but it is a form of acid, and it jumps over to the other one and just coats the outside of it because it's attracted to this plate. And again, it's because when the ions come off this throwaway metal of copper, they become positive, so they're going to be attracted to the negative plate. Kind of cool. Now this one that we see on the right, it's not the most clear image depending on your monitor. My monitor, it's not super obvious. But notice they have their positive terminal and they hooked it up to literally just a piece of copper, right? So that's just a piece of copper that they've got bent. This blue liquid looks like Kool-Aid, but it's not. It's actually some sort of acid bath kind of thing, right? So there's some sort of weird solution going on in there. And then they have what looks like a key that they've hooked up to the negative end, right? So the negative end is what you hook up the thing you want plated. From what I can tell from looking at this picture, it looks like they just dipped the bottom part of this key, just this part right here, into the solution. And you can see there's a little bit of like a reddish brown copper color that's forming on the bottom of this key. My impression from this, again, I don't know if this is from a video or what, I just found the picture on Google, but my impression from this is they didn't leave it in here very long, or the power source isn't very strong. Because really, when you do this, you should get a very substantial coating of copper on this key, because the copper is leaving the positive end and going to this negative end. Now, if you were to dip the whole key in there and just have like a little connection on the top, so it's still connected to the negative power source to complete the full circuit, you could actually plate the entire key in copper. And again, if you wanted to use something else to do this, like maybe you wanted your key to be plated in gold, you could use a piece of gold right here. You just might need a different kind of solution here. The solution is usually dependent on what you want plated. But still, you could coat your key in gold. That would be kind of cool. All right, we're done. That's it. So page 294, questions 1, 2, and then questions 4 to 8. I want you to get those questions done. Of course, it shouldn't take you too long. This video wasn't too long itself. So anyway, just another reminder, we're going to have a formative quiz on what we've learned so far this unit, just next class, right? So it's just going to be formative, not for marks or anything, but it's going to cover static electricity, current electricity, and cells and batteries as we've discussed today. One last thing I'll leave you with, if you're interested in that concept of electroplating, if you're interested in that concept, there's a YouTube channel that I actually quite enjoy. I might have actually shared it with you guys before like the whole school cancellation thing went on. But the old YouTube channel is a guy who basically refurbishes a bunch of old things. And one of the things he does in pretty much every single video, at least the ones I've seen, is he does use electroplating to plate things with nickel. Nickel is very commonly used to plate things, right? So when he does his electroplating, he uses, of course, nickel as the positive electrode and then hooks up whatever he wants, the negative one. Anyway, I'll stop rambling. The YouTube channel, in case you're wondering, is called Odd Tinkering. Quite one of my favorite YouTube channels for sure. If you want to check that out, please do. But apart from that, definitely get these questions done. And as always, if you have any questions, please let me know. Best of luck, guys. Talk to you soon.